Hi, I Dr. J. Manuel Janraja welcome you for the session on BGP stability features. Developing effective routing policies and configuring them correctly are at the core of building stability. BGP's attribute selections are the tools for building that core stability. In addition, following are the few BGP functions that can help provide a buffer against route instability effects. They are controlling route and cache invalidation, BGP route refresh, BGP route dampening. We will learn about them more as we progress in this session. The basis of any BGP conversation is the TCP connection that takes place between two BGP neighbors at the transport layer. The neighbor connection itself is based on the open message, which contains parameters such as the BGP version number. In addition, exchanged routing updates carry various attributes such as the metric, communities, and AS path. Whenever an administrator changes attributes or policies, traditional BGP implementations require that a BGP TCP session with its neighbors be reset or restarted before the modified routing behavior will take place. Unfortunately, every time the TCP session is reset, routing is interrupted. When a session is reset, the routing cache is invalidated and then routes disappear, and also the route instability cascades throughout the global internet. By the time the session is back online and routes and caches are re-established, real damage could result. Cisco routers introduced a mechanism called soft reconfiguration that enables administrators to configure and reconfigure attributes on the fly without killing an already established TCP session or manually introducing a route flap. Therefore, the routing cache is not cleared and the impact on the route is minimal. The offshoot of using soft reconfiguration is that it requires a set of unmodified routes from the specified peer or specified peers to be stored in local memory. The memory consumption required for utilizing soft reconfiguration with large pairs can be quite significant. A rule of thumb is that for each route learned from the pair, assume that 250 bytes of memory is required to store it. Another solution was introduced recently that removes the memory consumption associated with using soft reconfiguration. This alternative approach is referred to as route refresh capability. Route refresh capability utilizes BGP4 capabilities negotiation to facilitate a means of dynamically requesting that a peer re-advertise all the prefixes learned from the peer. This behavior is enabled by default in the current version of iOS and must be supported by the BGP peer router in order to use this feature. BGP route refresh removes the overhead of memory and CPU consumption required when using soft reconfiguration. It also allows all the prefixes learned from the peer to be examined and subjected to the new policy without requiring the BGP session to be reset. Another mechanism for controlling route instability is route dampening. A route that appears and disappears intermittently causes BGP update and withdrawn messages to be repeatedly propagated on the internet. The tremendous amount of routing traffic generated can use up all the link's bandwidth and drive up CPU utilization of the routers. Dampening categorizes routes as either behaved or ill-behaved. A well-behaved route shows high degree of stability during an extended period of time. An ill-behaved route experiences a high level of instability in a short period of time. Ill-behaved routes should be penalized in a way that is proportional to the route's expected future instability. An unstable route should not be advertised until there is some degree of confidence that the route has become stable. A route's recent history is used as a basis for estimating future stability. To track a route history, it is essential to track the number of times the route has flapped over a period of time. Under route dampening, each time a route flaps, it is given a penalty. Whenever the penalty reaches a predefined threshold, the route is suppressed. The route can continue to accrue penalties even after it is suppressed. The more frequently a route oscillates in a short amount of time, the faster the route is suppressed. Similar criteria are put in place to unsuppress a route and start re-advertising it. An algorithm is implemented to decay or to reduce the penalty value exponentially. The algorithm bases its configuration on a user-defined set of parameters. The following set of terms and parameters applies to the Cisco implementation. Number 1. Penalty. Penalty is an incremented numeric value that is assigned to a route each time it flaps. The second one is half-life. It's a configurable numeric value that describes the amount of time that must elapse to reduce the penalty by 1/2. Third one, suppress limit. It's again a numeric value that is compared with the penalty. If the penalty is greater than the suppress limit, the route is suppressed. Fourth one is reuse limit, a configurable numeric value that is compared with the penalty. If the penalty is less than the reuse limit, a suppressed route that is up will no longer be suppressed. Finally, suppressed route, a route that is not advertised even if it is up. A route is suppressed if the penalty value is greater than the suppressed limit. History entry is an entry used to store flap information. For the purposes of monitoring and calculating a route's oscillation level, it is important to store this information in the router when the route oscillates. When the route stabilizes, the history entry becomes useless and must be flushed from the router. The figure shown in this slide illustrates the process of assessing a penalty to a route every time it flaps. The penalty is exponentially decayed according to parameters such as the half-life. The half-life parameter can be changed by the administrator to reflect the oscillation history of a route. A longer half-life might be desirable for a route that has a habit of oscillating frequently. A larger half-life value would cause the penalty to decay more slowly, which translates into a route's being suppressed longer. The benefits of route dampening are noticed inside as well as outside an autonomous system. When BGP is injected into an IGP, it is important that BGP instability does not affect the internal routing in such a way as to cause a meltdown inside the autonomous system. This is where route dampening can be very useful. Routes that are flapping will be suppressed and prevented from being injected into the autonomous system until they show some degree of stability. In the figure shown, routes R1, R2 and R3 are injected from BGP into autonomous system. The up and down arrows next to R2 indicate that it is flapping. The routes are carried via iBGP or IGP depending on how the administrator is injecting the routes into the autonomous system. In either case, the oscillation of R2 create major overhead for the border router and on the interior routers. IGPs will flood and remove the route as long as the route is unstable. With route dampening, the ill-behaved route will be suppressed after reaching the suppress limit and will be prevented from entering the autonomous system. Route dampening can prevent unstable eBGP routes from being propagated to other peers. This can save on link bandwidth usage and processing overhead within border routers. If you are a provider with multiple customers using your services, it is important not to burden your own network and the outside world with instabilities that go on inside a customer's network. In the case where a provider advertises a customer's network as part of an aggregate, this is not an issue. The aggregate will be stable even if most of its elements are not. Within the provider's autonomous system, a customer's instabilities are a concern. When a customer's network cannot be aggregated, instabilities will be carried to the outside world. With dampening, the provider's border router suppresses customer routes that are flapping. One possible side effect of route dampening is that the customer will experience some short outages even if his routes become stable. Interesting. In the given figure, route R2 in the customer network is flapping. When the customer's ISP is running route dampening, R2 will be penalized and suppressed according to its level of oscillation. R2 could be dampened for minutes. Even if R2 stops oscillating, the penalty it had accumulated still might be far above the reuse limit, and it has to be decayed before the route can be used. In the meantime, some poor soul on the customer's network is pulling out his or her hair trying to figure out why some subnets can't be reached from the outside world. If administrators are unaware that the routes are being dampened, they might try to remedy the situation by some other means, which makes their routes flap even more and become more penalized. The better approach is to ask the provider whether he is receiving the routes, and if he is, check why they are not being advertised. Providers have strict policies and might not change the dampening behavior per the customer's request. What the provider can do is flush the history information of the routes being dampened to advertise the route. On the other hand, instabilities can be caused by the providers themselves, and the effect can be much larger. If a link carrying full routes between a provider and customer or a provider and another provider oscillates, the border routers will feel the impact. Suppose that you are getting full internet routes from multiple providers. Now imagine that 5% of these routes are toggling every 2 minutes. Your border router will not be able to handle this load at all. Without route dampening, it is difficult to determine what is really happening. All you know is that the process utilization on your border router is increasing rapidly. Route instabilities in the internet will affect everybody one way or the other. It is everyone's responsibility to minimize route oscillation by being more aware of the things they do and why they do to them. Well, that's it. We'll see more on building BGP peering session in the coming sessions. Thank you.